Good morning. I am Dr. R. Murli, Professor, Department of Mathematics, Dr. Ambedkar Institute of Technology, Bengaluru. I will be delivering lectures on the topic partial differential equations, which is under Module 3, Engineering Mathematics 2, with subject code 15 MA 21. In the previous session, we have defined a partial differential equation, or in short what is called a PDE, and how to form a PDE by the elimination of arbitrary constants in a given relation. As you are aware, the best way to remove constants is by differentiating the given expression, and because we are studying partial differential equations, we can eliminate constants by partially differentiating the given relation. And we have seen in the previous session that in our notations we consider z to be the dependent variable which is dependent on the two variables x and y. So, z depends on x and y, and we have the following partial derivatives. The first order partial derivative of z with respect to x, which is also denoted by z subscript x, is denoted by p. The first order partial derivative of z with respect to y, which is denoted by zy, is denoted by q. Then we have the second order partial derivatives, dou square z by dou x square, which is also denoted by zxx, is r. Then dou square z by dou x dou y, which is also the same as dou square z by dou y dou x. Using notations, this is zxy or zyx, this is s, and finally dou square z by dou y square, which is zyy, is denoted by t. Now, we have seen in the previous session that any PDE involving the partial derivatives p and q becomes a PDE of order 1, and a PDE that contains any of this, not necessarily all of this, one or more of the partial derivatives r, s and t becomes a PDE of order 2. So, we have illustrated examples where we eliminate arbitrary constants from a given relation. Now, in today's session, we will be concerned about the formation of a PDE by the elimination of arbitrary functions in a given relation. Now, as we mentioned just now, PDEs are formed by two methods. One, this was discussed in the previous session, where you remove arbitrary constants in a relation, and today we will see the elimination of arbitrary functions from a given relation. Now, in the case of arbitrary constants, observe that if the number of constants is equal to the number of independent variables, that is, say for example, two independent variables x and y, then we obtain a PDE of order 1. So, if the number of independent variables is equal to number of constants, you get a PDE of order 1. If it is more, if the number of constants is more than the number of independent variables, then we obtain a second order PDE or even higher. And in most cases, it is seen that the order of the PDE is number of arbitrary constants eliminated in the relation minus 1. For example, 3 constants are present in a relation, 3 minus 1 gives you a PDE of order 2, and so on. But if you eliminate arbitrary functions, the order of the PDE is exactly equal to the number of functions removed from the relation. And one more thing you should note, friends, is that when eliminating arbitrary constants, when you eliminate arbitrary functions, constants if present in the relation need not be removed. So, they can remain in the PDE as it is. Now, these notations are described in the board here. We take z as a function of x and y, dou z by dou x is p, dou z by dou y is q, then you have the second order partial derivatives r, s and t. Let me remind you again, first order PDE invariably contains both p and q, whereas a second order PDE can contain one or more of the partial derivatives r, s and the variable and the derivative t. Let us go to some examples. Formation of a PDE by the elimination of arbitrary functions in a given relation. The first example, form the PDE by eliminating the arbitrary functions in the following. The first example, z is equal to y square plus 2 into f of 1 by x plus log y. So, this is the arbitrary function to be eliminated, to eliminate the function f. So, because there is only one function in this, you should get a partial differential equation of order 1. That is to say, the partial differentiation, PDE should contain the partial derivatives p and q only. So, you don't go to higher order derivatives. So, what we do, differentiating the given relation partially with respect to x and y respectively. First, let us do the differentiation with respect to x. So, z in the LHS changes to dou z by dou x, which is also equal to p. In the RHS, the first function y square is a constant with respect to x, so that is 0. Then the derivative of 2 into f of 1 by x plus log y is like this. First, differentiate the function f, which will give you 2 into f dash, f will become f dash on differentiation. So, f of 1 by x plus log y reduces to f dash of 1 by x plus log y, and then the derivative of 1 by x plus log y with respect to x, where you have only 1 by x as the variable, and the derivative of 1 by x is minus 1 by x square. So, finally, the value of p becomes 2 into f dash 1 by x plus log y into minus 1 by x square. Let us call that equation 1. Now, take the same expression in that you see here, the expression for z, and differentiate partially with respect to y. When you differentiate partially with respect to y, z changes to dou z by dou y, which is also by notation equal to q. When you differentiate with respect to y, y square is the variable. So, derivative of y square is 2y plus, this differentiation is similar to the differentiation partially with respect to x. So, 2 into f of 1 by x plus log y changes to 2 into f dash of 1 by x plus log y into the derivative of 1 by x plus log y with respect to y, which is 1 by y. 1 by x is a constant which is 0. So, I get 1 by x plus 2 f q equal to 2y plus 2 f dash of 1 by x plus log y into 1 by y. Let us call that equation 2. Now, the aim in this problem is to remove the arbitrary function f. So, how to do that? Go to expressions 1 and 2. From equation 1, if you simplify, shift the x square to the LHS, you get, and the negative sign also. So, you get minus x square p equal to 2 into f dash 1 by x plus log y, and from equation 2, for easy simplification, shift the 2y to LHS. So, you get q minus 2y, and then shift this denominator y to the LHS, which gives you y into q minus 2y equal to 2 into f dash of 1 by x plus log y. Now, observe clearly that the RHS expressions in 3 and 4 are identical. So, you can just equate or you can divide and so on. So, because these two are identical, we can equate the two expressions. So, from 3 and 4, minus x square p equal to y into q minus 2y, or minus x square p equal to, multiply this y inside, yq minus 2y square, or equivalently x square p plus yq plus 2y square is the required PDE of order 1. Let us go to the next example. This again concerns the elimination of a single function f. So, again by our earlier notations, if we remove this f, I should get a PDE of order 1, meaning the partial derivatives present in the final expression should contain only p and q. This you must remember, friends. Do not try to differentiate the expression more than the required number of times. Now, differentiating the given expression partially with respect to x and y, let us first show the differentiation partially with respect to x. Observe that the expression for z contains two expressions, one e power ax plus by and the other f of ax minus by, both of which contain x. So, obviously, when you differentiate partially with respect to x, you need to apply the product rule. So, dou z by dou x equal to p will be first function e power ax plus by into f of ax plus ax minus by is f dash of ax minus by into ax minus by with respect to x is a, plus second function f of ax minus by into differentiation of e power ax plus by with respect to x is e power ax plus by itself into the differentiation of the power ax plus by with respect to x, which gives you a. And this, my friends, is by the application of product rule. You can observe that there is a common factor a in this expression. So, that is removed out to get p equal to a plus a into e power ax plus by into f dash ax minus by, plus this expression is replaced by the value z, which is the given expression. So, if you take a common, one expression contains the expression f dash and the second contains this expression, which is nothing but the given expression for z. Call that equation 1. Now, differentiate partially with respect to y. Again, observe that e power ax plus by as well as f of ax minus by contain the variable y also. So, you need to apply the product rule. So, when you apply product rule, dou z by dou y equal to q, first function e power ax plus by into f of ax minus by is f dash ax minus by into ax minus by with respect to y is minus b. Notice the negative sign, the coefficient of y is negative, plus second function f of ax minus by into differentiation of e power ax plus by is e power ax plus by itself into ax plus by with respect to y is equal to b, this constant. Again, I have b common in this, take this b common and observe that the second term in this is z again. So, that gives you q equal to b into minus e power ax plus by, minus sign is due to this minus sign is here, minus e power ax plus by into f dash ax minus by plus z. Let us call that equation 2. Now, how to form the PDE? Multiply equation 1 by b. Okay? Multiply equation 1 by b, you get bp equal to, you have already a outside. So, another b is multiplied into whatever is there in equation 1. So, it is ab e power ax plus by f dash ax minus by plus z. Multiply equation 2 by a, already you have q in a in equation 2. So, left hand side becomes aq you have b common factor outside in equation 2. So, if you multiply by a, it becomes ab again. So, it is ab into minus e power ax plus by into f dash ax minus by plus z. Finally, add equations 3 and 4 and observe that when you add, these two terms get cancelled because they are opposite in sign, leaving you 2z within the brackets. So, that bp plus aq becomes ab plus ab 2ab into z. You have 2z in this. So, that bp plus aq equal to 2abz is the required PDE. Now, these examples illustrate the formation of a PDE when one function is eliminated. Let us move on. Let us go to examples where you eliminate two functions. Okay. In the next example, eliminate the functions f and g, f and phi to obtain the PDE. So, what are the observations to be made? First observation, in this example, two arbitrary functions f and phi have to be eliminated. So, by our definition given earlier, because there are two functions, the PDE should be of order 2. You cannot get a first order PDE. So, it should be order 2. That means to say, not only you calculate P or Q, you also try and calculate R, S and T. R, S and T, as you see here on the board, are the partial derivatives with the second order partial derivatives with respect to x, y and y itself. Now, when a second order PDE is to be constructed, as far as the second order derivatives are concerned, every PDE need not necessarily contain all the values R, S and T. It depends on the given expression. Okay. Some PDEs may require only R, some may require two of them, some may require all the three and so on. In this example, we will see that one of the partial derivatives is not necessary, right. It comes by practice, trial and error will give you the PDE. You will then learn what are the partial derivatives to be considered in the equation, what are not to be considered to form the PDE. So, the order of the PDE will be 2 because there are two functions to be eliminated. So, we go through the usual process of differentiation. First, calculate the first order derivatives, differentiating the given expression partially with respect to x and y respectively. First, dou z by dou x equal to p, the derivative of y f of x, y is a constant with respect to x, so only fx becomes f dash x, so it is y into f dash x into the differentiation of the bracket term which is x with respect to x is 1, so that we do not write, plus in x and phi of y is a function of y which is a constant. So, you have to only differentiate the function x which gives you 1. So, that leaves you that first order partial derivative p as y f dash x plus phi of y. Next, go to the partial derivative with respect to y. Dou z by dou y equal to q. When you differentiate with respect to y, the first term y into f of x has f of x a constant term with respect to y. So, the derivative of y in that is 1. So, you get 1 into f of x plus in the second term like you defined, like you wrote for p, in x and phi y, only phi y is the variable. So, the derivative of x into phi of y with respect to y is x into phi dash of y. You do not stop here because there are two functions to be eliminated. So, you go to the higher order derivative also. So, let us go to the next partial derivative which is dou square z by dou x square, and I think my friends you know dou square z by dou x square is obtained by differentiating dou z by dou x again with respect to x. So, go to dou z by dou x here and differentiate that with respect to x. So, that gives you dou square z by dou x square. In this, the term containing x, this term does not contain x. So, that is 0 on differentiation, and y into f dash x, only f dash x is the variable. So, differentiating that with respect to x, you get y into f double dash of x. Now, this leaves out two more partial derivatives which are dou square z by dou x dou y, which can be obtained by differentiating dou z by dou y with respect to x, and that is denoted by s. And finally, dou square z by dou y square, which is obtained by differentiating dou z by dou y again with respect to y. So, as far as this is concerned, you go to dou z by dou y here and differentiate that partially with respect to x. So, that will give you f of x changing to f dash x and x into phi dash of y changing to phi dash of y only, because you are differentiating with respect to x. And finally, dou square z by dou y square is obtained by partially differentiating dou z by dou y or q with respect to y. So, that will give you f of x as 0, because it does not contain y, and x into phi dash of y on differentiation with respect to y partially will give you x into phi double dash of y. So, these expressions are illustrated in our next slide. As we mentioned, friends, you can observe this is your dou square z by dou x dou y f dash x plus phi dash y, and dou square z by dou y square, which by notation is t, is x into phi double dash of y. Now, how to form the PDE? You consider the sequence xp plus yq, the p obtained earlier in the previous slide. Take the value of x into p and take the value of p obtained. You can see that here. Take p, multiply it with x. So, you get xy f dash x plus x phi of y. Take q, multiply it with y on both sides. That give you qy is equal to q into y equal to y f of x plus xy phi dash of y, that you can see written here. You can see it is x into, this is p plus y into q, which is x into, let us rearrange. First I am writing these two terms, x into phi of y, then plus y into f of x, these two terms, this product and this product. That leaves out xy into f dash x, that is written here, plus xy into phi dash y, which is this term. So, that finally, you are left with x into phi y plus y into f of x. The last two terms have xy common, take it outside. So, you have xy into f dash x plus phi dash y. If you observe the sequence of partial derivatives, the first term is nothing but the given expression z. So, that is replaced by z, and f dash x plus phi dash y, you can see here, is the partial derivative s obtained from your differentiation sequence. So, that replace that by s, the first term marked here is the given z. So, that finally, you get z plus x y s or x plus y q equal to z plus x into y into s is the required PDE. Now, you should make the following observation in this example, that is that in your differentiation sequence, you have not made use of this partial derivative, correct. So, t is not used, neither is the value of r which was shown in the previous slide is used. So, by trial and error you get the PDE. So, this example requires you to calculate only p, q and s. The necessity of r as well as t does not arise, but this is not the case for all examples. Each example has its own requirements. Some may require, as I told you, r, some may require s, some may require all the three, and so on. As we go along, we can see the necessity of these partial derivatives. Let us go to the next example. Form the PDE given z is equal to f of x plus e power y into g of x. Here again, there are two functions f and g that are required to be eliminated from the expression. So, again f and g elimination will give you PD of order 2, will mean that you not only do PQ, but also you calculate RST. Again, let me remind you, there is no need to calculate all of them, that depends on the given expression. So, if you differentiate partially with respect to x and y, dou z by dou x will give you, first term contains x, f of x is transformed to f dash x, second term is e power y g of x, in which gx is the function containing x. So, on differentiation that gives you g dash of x. So, p becomes f dash x plus e power y into g dash x. Now, if you differentiate partially with respect to y, z is dou z by dou y, f of x is a constant with respect to y. So, that is equal to 0. In e power y gx, only e power y contains y, whose differentiation gives you again e power y itself into the multiplied function gx as it is. Go further. In this example, notice that there is no need to calculate R and S. If you calculate also, it may not be necessary in the final PD. So, we go to directly the partial derivative dou square z by dou y square, which is equal to t. And friends, let me remind you, dou square z by dou y square is obtained by differentiating dou z by dou y again with respect to y. So, go to dou z by dou y and differentiate that again with respect to y. You get e power y is e power y itself into g of x is a function of x, which remains as it is. For the required PD, observe that q and t are identical. So, q is e power y gx, t is also e power y gx. So, that q equal to t or q minus t equal to 0 becomes the required PDE of order 2. The observation to be made in this example, the partial derivatives R and S are not necessary in the formation. Let us go to the next example. A few examples now, one or two will show you the necessity of all the three second order partial derivatives to form the required PDE. In this example again, two functions f and g have to be eliminated, which will result in a PDE of order 2. Now, there is no harm in doing all the calculating all the derivatives, then you can consider only those derivatives which are necessary for the formation and ignore those partial derivatives which become non-essential in the sequence. So, first let us do the differentiation with respect to x. First order derivatives, dou z by dou x equal to p equal to f of y plus x will become f dash of y plus x, and then y plus x with respect to x is y is 0, x is 1. So, you get 0 plus 1, which we do not write here, that is understood. Then g y minus 2x is first, g dash y minus 2x, and then y minus 2x with respect to x gives you the extra minus 2, which is the coefficient of x. So, that on simplification p will be f dash of y plus x minus 2 into g dash of y minus 2x. Similarly, the partial differentiation with respect to y, which is q, will give f of y plus x is f dash y plus x, and then y plus x is 1 plus 0 with respect to y, plus g y minus 2x is g dash y minus 2x into derivative of y minus 2x with respect to y is 1. So, you get this. Because there are two functions to be eliminated, we go further, go to the next order partial derivative, which is dou square z by dou x square or r, which is obtained by differentiating dou z by dou x again with respect to x. So, if you differentiate this with respect to x, f dash of y plus x becomes f double dash of y plus x into y plus x again as described in P is 0 plus 1, then minus 2 g dash y minus 2x transforms to minus 2 g double dash y minus 2x into the differentiation of y minus 2x with respect to x, which is minus 2. Rearrange, minus 2 into minus 2 gives you 4, leaving you r as f double dash y plus x plus 4 g double dash y minus 2x. Let us go to the next partial derivative in the sequence. Dou square z by dou x dou y, which is s. Let me remind you again. Dou square z by dou x dou y is obtained by differentiating dou z by dou y with respect to x partially. So, go to dou z by dou y and differentiate only the x terms in this. So, f dash of y plus x becomes f double dash of y plus x, and g dash y minus x, y minus 2x transforms to g double dash y minus 2x into coefficient of minus 2x equal to minus 2. So, that finally s is f double dash of y plus x minus 2 into g double dash of y minus 2x. One more second order partial derivative remains in this sequence, that is dou square z by dou y square or t, which is obtained by differentiating dou z by dou y with respect to y. So, that is here. So, go to dou z by dou y and differentiate that with respect to y. So, f dash of y plus x changes to f double dash of y plus x, and g dash of y minus x minus 2x with respect to y is transformed to g double dash y minus 2x. So, that is written here. For the required PDE, we consider the sum of r and s. R, which was the derivative obtained here, f double dash y plus x plus 4 g double dash y minus 2x plus f double dash y plus x minus 2 g double dash y minus 2x. So, the sum of r and s will give you 2 f double dash y plus x plus 2 g double dash y minus 2x. That is because you have 2 f double dash terms here. So, f double dash plus f double dash is 2 f double dash. Then you have 4 g double dash minus 2 g double dash, which is 4 minus 2 equal to 2. So, that r plus s has a common factor 2, taking the common factor 2 outside, you are left with 2 into f double dash y plus x plus g double dash y minus 2x, which you can see is t that was obtained earlier. So, that it becomes 2t. Hence, r plus s equal to 2t is the required PDE of order 2. A very similar example to this is written here, which you can try. Find the PDE given z equal to f of y plus x plus g of y plus 2x. The final PDE for this expression is r plus 2t equal to 3s. Now, what you must observe in the example here is that it contains all the 3 partial derivatives, correct, r, s and t, whereas 1 or 2 examples showed earlier the necessity of finding some of the partial derivatives was not relevant in the problem. So, even in the example given here, you need to calculate all the partial derivatives r, s as well as t. Now, let us go to a similar example. similar to the example we illustrated now. Form the PDE from the relation z equal to f1 of y plus 2x plus f2 of y minus 3x. The only difference here is that instead of the functions f and g, you need to eliminate the functions f1 and f2. Again, there are two functions, so you should get a PDE of order equal to 2. So, that means to say again, you not only find PQ, you also try to find RST and then see what relations will exist between PQ, RS and T to give you the PDE. So, when you differentiate z with respect to x, P will be f1 of y plus 2x is transformed to f1 dash y plus 2x into 2 plus f2 dash of y minus 3x into minus 3, which on simplification gives you 2 f1 dash y plus 2x minus 3 f2 dash y minus 3x. Go to the next partial derivative, dou z by dou y equal to q, which is f1 dash of y plus 2x into y is 1 plus f2 dash of y minus 3x into again y is 1. We go to the next partial derivative, which is r, or dou square z by dou x square obtained by differentiating dou z by dou x again partially with respect to x. That gives you 2 f1 double dash y plus 2x into y plus 2x is 2 with respect to x minus 3 f2 dash becomes f2 double dash y minus 3x into partial derivative of y minus 3x with respect to x is minus 3. On simplification, this is 2 into 2 4 f1 double dash y plus 2x plus minus 3 into minus 3 minus plus 9 f2 double dash y minus 3x. Go to the next partial derivative, dou square z by dou x dou y, which is obtained by differentiating dou z by dou y with respect to x. So, go to q, differentiate that again partially with respect to x. So, you have f1 double dash y plus 2x into 2x is 2 plus f2 double dash y minus 3x into my y minus 3x is minus 3 with respect to x. That will simplify to 2 f1 double dash y plus 2x minus 3 f2 double dash y minus 3x. The last partial derivative in the sequence, dou square z by dou y square, which is t, obtained by differentiating dou z by dou y with respect to y. So, this partial derivative is again differentiated with respect to y. So, you get f1 double dash y plus 2x into 1 plus f2 double dash y minus 3x again into 1. So, that is illustrated here. For the required PDE, you consider the sum of r and s, r plus s, which is r plus s is here 4 plus 2 6 into 4 plus 2 gives you 6 f1 double dash y plus 2x plus 9 minus 3 again 6 f2 double dash y minus 3x, which gives a common factor of 6 times f1 double dash y plus 2x plus f2 double dash y minus 3x, but f1 double dash y plus 2x plus f2 double dash y minus 3x is t from this derivative here. So, you get RHS as 6 into t, or r plus x equal to 60 is the required PDE. A similar example is written here for practice. Form the PDE given z equal to f1 of y minus 2x plus f2 of 2y minus x. The final answer is 2r plus 5s plus 2t equal to 0. Let us go to the Next example, form the PDE given z equal to f of x plus ct plus g of x minus ct. Now friends, do you observe any change in the variables in this? Of course, this example also contains two arbitrary functions f and g. So again you should get a PDE of order 2, but observe that the independent variables are not x and t, but x and y, but x and t. So when you do the partial differentiation sequence, your partial derivatives will be dou z by dou x, not dou z by dou y, but dou z by dou t, then dou square z by dou x square, not dou square z by dou x dou y, but dou square z by dou x dou t, and finally dou square z by dou t square and not dou square z by dou y square, because instead of the independent variables x and y, you are given the independent variables x and t. So how to go about the PDE? Differentiating the given relation partially with respect to x and t, we get first with respect to x, z transforms to dou z by dou x, no notations, remember, notations are valid only for x and y. So we will keep the partial derivatives as it is. So dou z by dou x is f of x plus ct is f dash of x plus ct into 1 plus g of x minus ct transforms to g dash of x minus ct into 1. Let us do the differentiation with respect to t. Let me remind you again, dou z by dou y is not valid in this example because the second independent variable is t and not y. So instead of dou z by dou y as in the previous examples, it should be dou z by dou t. So dou z by dou t is first f transforms to f dash of x plus ct into derivative of ct with respect to t is c plus g of x minus ct transforms to g dash of x minus ct into partial derivative of x minus ct with respect to t is minus c. Both these give a common factor c, which when removed gives you c into f dash of x plus ct minus g dash of x minus ct. Let us go to the second order partial derivatives. First, dou square z by dou x square, which is obtained by differentiating dou z by dou x here with respect to x. That will give you f dash of x plus ct changing to f double dash of x plus ct plus g dash of x minus ct changing to g double dash of x minus ct. Let us call that equation 1. Let us go to the next second order partial derivative, dou square z by dou t square, which is obtained by differentiating dou z by dou t here again with respect to t. So if you differentiate with respect to t partially, you get c into f of x, f dash of x plus ct is transformed to f double dash of x plus ct into ct with respect to t is c, 1c here, plus then minus g double dash x minus ct into x minus ct with respect to t will be minus c. That gives you two c terms, again here common, which gives you c square into f double dash of x plus ct plus g double dash of x minus ct, but observe that f double dash of x plus ct plus g double dash of x minus ct is nothing but dou square z by dou x square. So that dou square z by dou t square here becomes c square into this expression is dou square z by dou x square from equation 1. So that dou square z by dou t square equal to c square into dou square z by dou x square is the required PDE. What you must observe is, in this example, the partial derivative dou square z by dou x dou t is not necessary for the formation of the PDE. One more example where again the independent variables are x and t. So, form the PDE given z equal to x into f of x plus t plus g of x plus t. So, again two functions f and g are to be eliminated. First point, which will give you a PDE of order 2. Second, the independent variables are not x and y, but they are x and t. So, we continue the differentiation as usual. First, dou z by dou x, which is the partial differentiation with respect to x of this, but observe that x into f of x plus t has two terms containing x, which are this x and f of x plus t. Apply product rule. So, it gives you x into f dash of x plus t for f of x plus t plus f of x plus t into 1 using product rule plus g of x plus t is transformed to g dash of x plus t. Then dou z by dou t, when dou z by dou t is obtained, x is a constant with respect to t. So, product rule is not necessary. So, you get x into f of x plus t transforms to f dash of x plus t plus g of x plus t is transformed to g dash of x plus t. Go to the second order partial derivatives. Dou square z by dou x square by differentiating dou z by dou x partially with respect to x again. So, apply product rule for the first term, which is x into f dash is f double dash of x plus t plus f dash of x plus t into 1. Then again this f of x plus t becomes f dash of x plus t, and g dash of x plus t transforms to g double dash of x plus t. That is, you can see illustrated here, because it contains two f dash of x plus t terms. Finally, you get 2 times f dash of x plus t. This f dash of x plus t is due to the product rule, and this f dash of x plus t is due to the f of x plus t present in dou z by dou x. Then dou square z by dou x dou t, which is obtained by differentiating dou z by dou t with respect to x. How to do that? Go to the expression for dou z by dou t here and differentiate that partially with respect to x. So, first term requires product rule, x f double dash x plus t plus f dash of x plus t into 1 plus g double dash of x plus t. And finally, dou square z by dou t square, which is obtained by differentiating dou z by dou t again with respect to t, that is here. So, differentiate this with respect to t partially. So, x into f dash of x plus t present, this with respect to t changes to x into f double dash of x plus t, and g dash of x plus t is transformed to g double dash of x plus t on differentiation. So, that for the required PDE, you take the sum of dou square z by dou x square plus dou square z by dou t square, these two terms, which gives you x f double dash plus x f x double dash 2x f double dash, then plus 2f dash here, which is written as it is here, plus g double dash plus g double dash here, which gives you 2 times g double dash. Observe that if you take 2 as the common factor, whatever remains is dou square z by dou t square, that is obtained here. So, that finally, the PDE is dou square z by dou x square plus dou square z by dou t square equal to 2 into dou square z by dou x dou t. So, friends, In today's session, we have seen the formation of a PDE by the elimination of arbitrary functions in a given relation. Notice that the order of the PDE is exactly equal to the number of functions eliminated from the relation, not like when you did constants where the order of the PDE was equal to the number of independent variables. If there are two independent variables, you get a PDE of order 1. In constants, when there are more than two independent variables, you get a PDE of order more than 1 also. But in functions, the order of the PDE is exactly equal to the number of arbitrary functions in the relation, and when you eliminate functions, there is no need to eliminate constants that are present in the given relation. In the next session, we will look into some more examples where the given expression will be in another format, not like the ones you saw today. Thank you, friends. We will continue in our next session.